Hello everyone, and welcome to this video on thermometry. Specifically, in this video we're going to talk about Kelvin and the absolute temperature scale and how William Thompson came up with that concept. So William Thompson lived back in the 19th century, the mid-19th centuries. They said that he was an outstanding scientist and engineer. They said also that the first half of his life he could do no wrong, and the second half of his life he could do no right. Well, in the first half of his life he came up with this concept of absolute zero. And what would happen if you were able to reach absolute zero, temperature where it's completely zero? What is that? And back then, as we saw earlier with thermoscopes, they had gas type thermometers where the expansion and contraction of a gas was directly proportional to the temperature. So that's how they actually measured temperature in the laboratory, was using different gases and the expansion and compression or contraction. So if you have a fixed mass of gas in a container and you expand it, the temperature will change. If you compress it, the temperature will change in the other direction. This was discovered by two people, Charles and also Gaylussac. They came up with these concepts, and so therefore the law is known as the Charles-Gaylussac law. So for a gas that has no water vapor in it, they found that the temperature is directly proportional to the volume, or the change in temperature is directly proportional to the change in volume, if you are able to hold the pressure constant. So for a fixed mass of gas, you can divide the volume by mass, and then we'll get another concept or another variable. So we're looking at a container that has a fixed amount of gas. You're not adding any mass to it or taking any gas out. And that brings us to the concept of specific volume. Specific volume is the volume per mass of a substance, and if you do the inverse, it's actually the density. So you can think of it this way. It's the amount of volume, or how much volume, that 1 unit kilogram or 1 kilogram or 1 unit mass of a substance will take up. So if I had a kilogram of dry air, how much space would that take up? That's what specific volume is. So we can do that. We can do that calculation for standard temperature and standard pressure. Standard temperature is 15 degrees Celsius, or that would be 288 degrees Kelvin. And then the pressure is 1013.25 millibars, which is 1013.25 pascals. And we're going to look at how much mass 1 meter cubed of air takes up. And we're looking at dry air specifically. So if we do the calculation, we can use the ideal gas law and solve for mass. We've got pressure, we got volume, and also we got temperature. And we do that calculation, and we come up with 1.2 kilograms. So 1 meter of air takes up 1.2 kilograms. So the density of air would be that mass divided by that volume. The mass we calculated was 1.2 kilograms, and the volume is 1 meter. So your density is 1.2 kilograms per meter cubed. Now, specific volume is the amount of volume that 1 kilogram of air would take up. It's just the inverse. So if we do the inverse of density, we'll have 1 meter divided by 1.2 kilograms, which gives you about 0.81 meters cubed per kilogram. So at standard conditions, 1 kilogram of air takes up a little bit less than 1 meter cubed, about 0.8 meter cubed of volume. So we're going to use this concept of specific volume and put it into the Charles-Gaylussac law. And when we do that, we have a relationship between temperature and specific volume, the inverse of density. So this equation looks a lot like a line. It's actually linear. Temperature is proportional to specific volume. So if that's the case, then, as you do with lines, you can actually come up with an equation for that line if you have some known values. So let's stick some known values in here. Let's stick in the known value for the ice point. You know that the temperature at the ice point in the Celsius scale is 0. So we'll put in the temperature of the ice point. And we actually have done experiments. We can figure out how much specific volume you have at the ice point, the specific volume of a gas, a particular gas. In this case, we're talking about dry air. So there's our equation. And it says that at a particular temperature, you can figure out the specific volume, or vice versa. Now, the problem is, though, we know what the ice point temperature is, and we know that the specific volume at the ice point, we figure that out experimentally. But what is K? This is a constant. This is the slope of the line. And we're going to have to come up with that somehow. So we're going to use the Celsius scale, because we know what the temperature is at various points, and we know what the specific volume is at specific points. For example, we already said that at the ice point, at a temperature of 0, you have a certain specific volume, which we're going to call IPs, the specific volume at the ice point. Likewise, also, we know that at the steam point, or boiling, the temperature is 100 degrees Celsius, and we're going to call that the specific volume at the steam point, SP. So using that, we can actually come up with a value for K. We can figure out what the slope is. So here we are. We put those values into this equation, and then we solve for K. We haven't put in any values for the steam point yet, or for the ice point. We'll leave it at that right now. So that is our value of K. We're going to put that back into the equation that we had earlier that gave us a relationship between temperature and also specific volume. So all we're doing is substituting K in, the K that we just came up with, back into that equation. So here we go. We're going to combine those two, and it looks a little bit messy, but it gives us a temperature. Remember, at the ice point, we have 0 degrees Celsius, and at the steam point, the temperature is 100, so we'll stick those values in. And then we have the difference in the denominator. We have the difference between the steam point and the ice point. We've had that before. We'll put that in there. And here's our new equation. This is getting a little bit complicated, isn't it? But this is what Kelvin theorized. He said, what if your volume of a gas contracted to 0? You could compress it all the way down to 0, a constant pressure process, bring it all the way down to 0 volume. What would the temperature be, hypothetically? So we're going to stick some numbers in. As I said, we know the value of dry air at the ice point and the value of dry air, the specific volume of the dry air at the steam point. So we'll stick those in, and we've got the temperature 100 we had before, and we're wondering if the volume went all the way down to 0, specific volume, and that's what you see on the top. You see the 0 there. What would the temperature be? And this is what Kelvin did. Linearly, he went back and figured out that the temperature where you have 0 specific volume, or 0 volume, it would be a temperature of minus 273.15 Celsius. So that is absolute 0. So Kelvin came up with the absolute 0, the absolute temperature scale, with 0 being the reference point, which was absolute 0, and it's where if an ideal gas were cooled to 0, its volume would be 0. So here's a couple different ways of looking at absolute 0. These are definitions. It's the 0 point on the Kelvin scale, of course, and also if you linearly extrapolate back to a point where you had zero volume, you would have zero temperature, and that's under constant pressure. And then in this case, no heat energy remain in the substance, but the molecules move as required by quantum theory. So, is this possible? Do we ever see absolute zero here in North Dakota? Sometimes it feels like it, but experimental scientists or physicists have achieved very low temperatures, 100 picokelvin, which is a world record back in 1999. If you want to look it up, you can look that up. But as you know, most gases become liquid or solid at very low temperatures, so it's not as easy as it sounds, of course. And that concludes our discussion of Kelvin and absolute zero.